Hello, everyone. Continuing on our problems related to growth and decay and separation of variables. In my last video, we talked about the exponential growth and decay model. And then we talked about Newton's law of cooling. So we looked at problems of population growth, radioactive decay. Then we looked, the last thing I did in my last video was Newton's law of cooling, and did an example for an application for Newton's law of cooling. So today, I will be now continuing on more problems, and then finally, I will be finishing this lecture with logistic differential equations. So let's look at another differential equation problem, which is called a wildlife population. And you will see that this is very similar when you write down the differential equation. It's very similar to our Newton's law of cooling. Okay, so let's start here. The rate of change of the number of coyotes, say I'm writing that the number of coyotes is by n of t, in a population is directly proportional to 650 minus n of t, where t is the time in years. Let me read it again. The rate of change, okay, the rate of change of the number of coyotes in a population is directly proportional to 650 minus the number of coyotes. So where t is the time in years. So this first line of this problem basically says, if my n is the number of coyotes, so that means dn over dt is proportional, directly proportional or proportional to 650 minus nt, and it is the rate of change. Okay, so what does that mean? It is k times 650 minus n. Okay, this is our differential equation. And if you notice, it is very similar to our Newton's law of cooling. Let me show you that. There it is, Newton's law of cooling. Now, only thing over here has happened is that our variable, instead of being temperature of an object, is now this variable is the number of coyotes. And the difference, where my y minus t, this represented the difference in the object and the temperature of the surrounding medium, is actually given to us by that, the expression 650 minus n. You see that? So similar to Newton's law of cooling. Okay, now we're going to solve this problem. We want to find the solution also, okay? Because as you read the problem, it says, definitely we have to find the solution of this differential equation. And before I do that, let's continue reading the problem and then come back over here. Okay, it says when time is 0, that means when we started to look at the number of coyotes, the population was 300. And in two years, the population increased to 500. The question is, what was the population, or find the population when it was 3 years? To find this population, that means the population is the number of coyotes. I want to find n. I want to find n of t here. Now to find this n of t, remember this n of t is nothing but this n. This is the solution to this differential equation. So we have to first solve this differential equation. It's a very similar way we did in our previous Newton's law of cooling. So let's start it. So to find the solution of the above differential equation, we are going to use the separation of variables. Okay, let's get the n's and the t's together. So it's 1 over 650 minus n dn equals k dt. Then we will integrate both sides of this equation. So what are we going to get? Natural log of 650 minus n. Now remember, this one will have a negative in the front. Okay, because when I take the differential of this, I should get this. So which is negative natural log of 650 minus n equals kt plus a constant. Now I'm going to take the negative on the side. Natural log of 650 minus n equals negative kt, negative a constant. Okay. Now, so that means 650 minus n equals e to the power negative kt negative c, which I can write as e to the power negative kt times e to the power negative c, or this can be a constant e to the power negative kt. So it's 650 minus n equals c times e to the power negative kt. Okay. Okay, so just to make it a little different, I can write this as, so C1 does not matter. It's a constant, guys. If I want to write C1, I can write C1 does not matter, okay? Now, that means n equals 650 minus C1 e to the power negative kt. So this is my general solution, okay? Now what you're going to do is, you want to find the C's and the C1 and K. So I want C1 and I want to find K. Now it says when T is 0, population is 300. Let's do the math. So 300 equals 650 minus C1 e to the power 0, or we get negative 350 equals negative C1 e, that means 1. E to the power 0 we all know is 1, or my C1 is 350. Okay, so what is the solution? N is 350. Where is my N here? Oh, sorry, 650. Let's write it down again. (650) minus 350 e to the power negative kt. Okay. Now, notice I forgot to mention that when I took the 650 minus n, here I am assuming, okay, this is important. I removed this absolute value, forgot to mention here. Let me repeat this one. I am here assuming that the population here, that 650n is less than 650. That is 650 minus n is greater than 0. Important to keep in mind, okay? That is my assumption, that I'm assuming this, otherwise I could not have written 650 minus n like that, because it's an absolute value, remember, okay? So now we've got this formula, now we need to find my little k. Now to find this k, what are we given? The time is 2 years, the population increases to 500. So when t is 2, the n, that is the number of coyotes, is 500. So we're going to say this is 500 equals 650 minus 350 e to the power negative 2k. Now doing the math, what are we going to get? We get this one is negative 150 equals negative 350 to the power negative 2k, or 15 over 35, which is 3 over 7, equals e to the power negative 2k, or k is approximately, just take away. So I hope you remember this is negative half. Okay, I'm just going to take the exponential out first, negative half. Okay, let me just do it again. Just not be in a hurry, just show you the little steps. So it's natural log of 3 over 7, negative 2k, negative half. Natural log of 3 over 7 is k. Our k is approximately 0.4236. Okay, so my number of coyotes now is the formula is 350 e to the power negative 0.4236 t. We want to know when the population t is 3. So when t is 3, substituting 4236. No, take this number here. So n is 650 minus 350 e negative 0.4236 times 3. Approximately n is 552. So that means after 3 years, the coyote population is 552. Okay, now what we have been doing till now was our exponential growth models and everything, okay? Now notice, in our exponential growth model, we are saying that the rate of change of the variable y is proportional to the value of y. So if the exponential growth happens, remember the formula of the graph with it. Exponential growth means it just continues to grow unlimited. But in reality, there are going to be not unlimited resources, right? The resources are limited. So that means there's a point at which the population, suppose it's a growth population model, it's not going to grow. There's going to be a carrying capacity there, okay? So what it simply says, there exists some upper limit past which the growth cannot occur. This upper limit is called the carrying capacity, which is the maximum the population can be sustained or supported as time t increases. And that's where we are getting a more realistic picture. Because if you want to apply some models we have learned here, like exponential growth and decay model, we wanted it to be a little bit more realistic with what's happening in the real world. And logistic differential equation takes that into perspective. And it says that suppose if I'm applying this model, exponential growth model, say to a population, there will be a carrying capacity beyond which the population will not grow. And that's, as I said, logistic differential equations. So what is this model? A model which often describes this type of growth is the logistic differential equation. And this is given by this formula, dy by dt equals k times y, 1 minus y over L. K, now here, k and L are the two constants. They're positive. A population that satisfies this equation does not grow without bounds, but approaches the carrying capacity L as t increases. Okay, this time I'm not going to go through the whole process of finding the solutions. I'm just going to take the solution because our more important aspect over here is to apply this logistic differential equation in solving it. So we're going to take this, differential equation Again, we'll be doing the variable separable form. Let me tell you that. We'll be applying the variable separable form and doing the whole process again. So we are just going to apply this solution. And then when you apply this variable separable, you will actually end up getting this solution. So the solution for the above equation is 1 minus L over 1 plus B e to the power negative KT, where B, K, is the constant, and L, remember, is the carrying capacity. So if you're given a problem, you will be given the carrying capacity. Okay, from the above equation, so this equation, we see that if the Y, is between 0 and the capacity, carrying capacity, then the differential equation is positive. In other words, when Y over L is a proper fraction, then this is always, the differential equation is positive and the population will increase. On the other hand, if the Y, that is the looking at the population, if that Y is greater than the carrying capacity, then dy by dt is always, is negative and the population decreases, okay? And the graph of this function is called the logistic curve. Okay, this is the more realistic, scenario of a given population, say, population model. And notice, very long time ago, we talked about horizontal asymptotes. So this carrying capacity at Y equals L is a horizontal asymptote to our function here, okay? So when T approaches infinity, Y is approaching L. Just to remind you, we have done all these things and they're now being put more from a real life perspective. Okay, let's do one example on a logistic differential equation, and I'm going to apply it to an elk population. Let's read the problem. A state game commission releases 40 elk into a game refuge. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 4,000 elk. That means that's the carrying capacity. The growth rate of the elk population P is given by this logistic differential equation model, where the population P started at 40 and it can be only going till 4,000. And T represents the number of years. So the first question we would like to is write a model for the elk population in terms of T. When I'm saying this word, write a population for the elk population, I mean, find me the solution of this differential equation. That's what I'm simply saying, nothing else. Okay, and when I'm saying this, in other words, let's go back here. I need to find the B's and the K's. And I get this model, okay? So let's write it down first. What we know from our previous 2 slides here, that P of T is given by L, remember, it is L over, let me see if I've written it correctly. No, this is not right, yeah. That's the solution, L over 1 plus B e to the power minus KT. My fault, guys. I just want to make sure that this is written, and I'll try to also correct it in my notes, which I have already posted for you guys. Okay, so let's go back here. So it is L over 1 plus B e to the power minus KT. Now remember, my L is 4,000 from here. 4,000 over 1 plus B e to the power negative KT. So to find this model, what I need to do is find the B's and the K's. And now what is given to us? So let me write it down. P is 4,000, 1 plus B e to the power negative KT. So when my t is 0, population was what? 40. And when my t is, and after 5 years, notice from here, t is 5, the population is 104. Okay, so let's go ahead, substitute here. So P is 40 when t is 0. It's 4,000. 1 plus B, or 1 plus B is 4,000 over 40, which is 100, or B is 100 minus 1, which is 99. Okay, so we got the B. Now, when we got the B, so what is now this now? So P is now 4,000, 1 plus 99 e to the power negative k t. Now it says t is 5. So t is 5, population is 104. So when t is 5, I'm just getting here, 4,000, 1 plus 99 e to the power negative k t is 5. So once again, it's a simple calculation, and I will let you guys do this. Just show you a little bit one of this. 1 plus 99 e to the power negative 5k equals 4,000 over 104. And so then just go ahead and do it. K comes out to be approximately 0.194. Okay, so you can do the rest of the work. Okay, so what is our population? P is 4,000. 1 plus B was 99 e to the power negative 0.194 t. Now, the question is, find this model to estimate the population after 15 years. What does that mean? Now, remember, P of t, I've been writing P, it's, I can write this as P also, it doesn't matter. So P of t is given to be what? 4,000, 1 plus 99 e to the power negative 1.94 t. So that means when P of 15 is 4,000, 1 plus 99 e to the power negative 0.194 times 15, approximately 626. So once again, when we do a problem, what are we going to do is we are going to, so the solution basically, which I was, for this problem was going to be done here. I just ended up doing it on this page, guys. Okay, so I'm going to give you some practice problems for these applications. And then, once you've practiced them, we will look at other scenarios too. Okay. Thank you, guys. Work hard and make sure you go over the examples and then go ahead and apply your practice problems. Thank you.